Okay, so hello and welcome to the webinar on VisionMaster. My name is Dmitry Mikitenko. I'm a pre-sales engineer at Hikrobot, and I will guide you through VisionMaster basics today. Our session will be divided in three parts. In the first part, we will discuss the concept of a solution, which is the core element of the entire VisionMaster software framework. Then we will continue with an introduction to the VisionMaster interface to help you become familiar with its panels, menus, and general settings. And finally, I will show you how to design a simple solution for measuring distances. And then hopefully we will have some time for questions and answers. So what exactly is the solution and why is it so important? The solution is the main structural object in VisionMaster that contains all information related to a specific machine vision task. Only a small number of parameters exist at the application level. Almost everything else is stored within the solution itself. Even solution switching settings are part of the solution data. All global resources, including communication parameters, runtime user interface configuration, global scripts, and image acquisition settings, are all stored within the solution file. The key advantage of this design is high portability. Because all critical data is packaged together, a solution file can be easily transferred between environments while retaining full configuration consistency. However, this approach also requires careful planning, especially when multiple switchable solutions with typical configurations are needed in a production environment. In addition to global resources, each solution includes data processing algorithms or flows, depending on context. A procedure represents a single logical entity that can be triggered to perform a specific vision task. You can think of a procedure as of a substantial part of a machine vision algorithm. Procedures are built from modules, also called vision tools, that execute individual data processing steps. A module instance is, therefore, the smallest logical unit within the solution. A procedure's behavior is entirely defined by the modules it contains and the way they are interconnected. The execution order is determined by the arrows linking the modules. You can see it on these examples. Each module has input and output parameters, and the output of one module can serve as the input to any subsequent module in the procedure, provided the data types match exactly. A procedure can also include variables that can be bound to module inputs and outputs. This adds flexibility for data transfer within the procedure and, through global variables, enables data exchange between procedures. As shown in the example procedures on this slide, modules can form long sequences, potentially with multiple branches. Loops are not permitted in the main procedure flow, but a special module type called group can have its loop mode enabled, allowing it to iterate the modules contained within in the same way as a conventional loop you would find in a programming language. As I already said, modules are the core components of any procedure. Each one serves a specific purpose, such as image transformation, analysis, data transmission, or interaction with hardware. For example, a template matching module identifies a defined pattern within an image, while a send data module transmits results to an external device or control system. There's more than 150 modules in the VisionMaster, so you can pick appropriate one for many tasks. The combination of modules forms the complete logic of the algorithm implemented within a procedure. The VisionMaster user manual serves as an excellent reference for the detailed information on each module and its parameters. So I obviously advise to check uh, check it before using any specific module options. Okay, so let's continue. Now it's time to take a closer look at the VisionMaster interface and review its main functional areas. The VisionMaster interface is organized into several key areas. The menu bar for system commands, the quick tools for access to global functions and frequently used controls, the flow editing area for building algorithms, the image display area for visualization, the toolbox with vision modules, the history panel for result view, and the status bar showing performance data. This structured layout helps users navigate efficiently and maintain clarity when developing solutions. It is quite convenient. Let's have a closer look at these functional areas. The file menu manages solution files and related assets. It provides options to create new solutions, open existing ones, or load sample projects. You can save current solution, and while doing so, password protection can be applied, like that. You can set password from the same save dialog as shown here. You need to press that encryption option button for that. The solution can be exported as the code packaged in Visual Studio Project using C# or C++ programming language for further integration. It's done with that export algorithm code menu element. It is also possible to import procedures from other projects if they were exported previously. These functions enable the basic operations within the solution. The settings menu governs both system-wide and solution-level configurations. Here you can enable encryption to configure role-based access and define user permissions. Like that. You need to encrypt the project. Then you will have an option to enter administrator's password for the solution file and also optionally enable other roles. With this role-based access enabled, the user will be prompted to select appropriate predefined role and enter password to access the solution with specific level of permissions. And these permissions can be configured for one of the roles. In the same menu, it's possible to configure software behavior at startup and during execution, control automatic saving, and set solution switching preferences. It also includes strategies for resource allocation, image rendering, and saving, which are important for performance tuning. The Tools menu contains configuration and maintenance utilities. It includes calibration guide, board generation tool, and diagnostics tool for troubleshooting. The module parameter tool provides a detailed view of each module's input, output, and run parameters, showing names of the corresponding objects accessible via SDK and their current values. It looks like that. This tool is handy for secondary development as it allows developers to conveniently reference parameter mappings and retrieve values through the code. Access to the module parameter tool is restricted to only a specific license key types. Another important tool worth mentioning is the version switch assistant, allowing switching between multiple installed VisionMaster versions. It is particularly useful when working with both PC-based and embedded VisionMaster environments, because these versions are not like mutually compatible. So only one can be active at a time. The system and help menus give access to several monitoring and support features, including software logs, communication management, camera setup, and quick links to documentation, both local and online. Help menu also provides version information and links to Hikrobot official resources. The visual toolbox contains all vision tools grouped by category: acquisition, measurement, recognition, defect detection, image processing, communication, and others. Users drag and drop these modules into the flow editing area to construct the algorithm logic that defines the solution. In this short video, you can see the procedure being built with 3 modules. And they are parameters adjusted to achieve desired, say, result for quality control. In this particular example, images loaded from files are used, and later today we will see what options are there for image acquisition. In general, what you will see here is a typical no-code approach when you just modify parameters, organize modules in sequence, and observe results. That's what typical VisionMaster procedure design workflow looks like. So what about the flow editing area? It is where the procedure logic is built. Each module is represented as a block connected by arrows and define data flow and execution order, as I already said. The interface supports quick navigation between modules and shows their last execution status through color indicators, either green or red in case of failure, and if the module is disabled, it will be grayed out. It makes easier to debug and maintain procedures. And the context menu can be conveniently used to search modules by their IDs, and it will find module in any procedure in a solution, not only the currently open one, and it's possible to quickly add modules to the procedure using this menu. Each module has configurable parameters divided into basic, run, and result categories. Basic parameters define inputs such as image source or ROI settings. Run parameters determine algorithm behavior and performance and are highly specific to each module, of course. The results section defines how the output is displayed on the rendered image, and sometimes offers options for additionally filtering results for further processing. This structure of parameters ensures consistent configuration across most modules, especially those that operate on image data. So regardless of which module you're about to use, you will know where to find this or that parameter, which category it belongs to. The image display area provides visual feedback for inspection results. Users can zoom, switch between views, and analyze pixel coordinates and intensity values. Overlay layers enable complex result visualization, while right-click actions allow saving images. It is also possible to add to cross-share guidelines to measure, for example, something, or check if a specific object appears on a kind of expected part of an image. Image display options can be configured at the procedure level to show the rendered output of multiple modules on a single image. So multiple rendering data will be overlaid and displayed simultaneously, adding convenience for visual inspection. The Quick Tools bar provides fast access to the most frequently used commands. It includes shortcuts for saving, opening, and undoing actions, as well as access to global solution entities such as cameras, variables, communication settings, triggers, and script. Operators can also start or stop solution execution, open the runtime interface builder, or use comprehensive configuration to adjust parameters of multiple modules scattered across different procedures from one single window. Uh, Comprehensive configuration feature is also restricted to specific license key types, so it's not available with every possible dongle or license key. And the history panel displays module outputs over time. The current result view shows data from the latest execution, while the history view allows comparison with previous runs, which is useful for procedure debugging or fine-tuning. And there's also Help tab, providing quick reference for module operations. Of course, not as extensive as sections in user manual. And in the bottom part of the VisionMaster interface window, there's a status bar providing live feedback on flow configuration, execution time, and zoom level in the editing area. It is particularly useful for monitoring performance during solution development tuning. Clicking on the flow execution time opens a window with detailed execution times for all modules within the procedure. So it's handy if you need to see which are the slowest ones or which maybe limit the overall execution performance, which are the bottlenecks for identifying these bottlenecks. Up to this point, we have focused on the structure of VisionMaster solutions and the key elements of the user interface. With this foundation in place, we can now move from concepts to practice. And in this section, we will walk through a concrete measurement example showing how individual modules are combined into a complete working distance measurement solution in VisionMaster. This example is based on a simple but rather representative inspection task. The goal is to measure the horizontal and vertical distances from the center of a reference mark to two orthogonal edges of the battery cell and to calculate the angle between those edges. The measured values are then compared against predefined reference values to determine whether the part meets the specified criteria. I hope on this image you can see the left edge. It is pretty dark, I'd say, so not that easily visible, but it's there. And here is that cross mark, which will be used as a reference point. So at a high level, a measurement solution in VisionMaster should follow a consistent structure shown on this slide. More or less. There are always exceptions, of course, but in general, this is conceptually the right way to build it. Image acquisition provides the input data. Locating tools establish stable reference features, and measurement modules calculate the required geometric values. When needed, image-based results can be converted into physical units using calibration or scaling factors. We will not touch this topic today, but hopefully in the future there will be another webinar on that. And finally, measurement results can be evaluated, formatted, and output through various channels such as on-screen visualization or data exchange communication interfaces, depending on system requirements and the integration demands. This slide shows the measurement solution designed to address the requirements defined earlier. It follows that recommended structure just discussed and illustrates how specific VisionMaster modules are arranged to meet the measurement requirements. The flow starts with image acquisition, as you can see, followed by template matching to locate the reference feature, the crossmark. Position fixture is then applied to adjust subsequent regions of interest, ensuring consistent output of line search modules. Based on identified features, point-to-line and line-to-line measurement modules compute the required distances and angle. The final steps handle result evaluation and data formatting in preparation for output. Let's check parameters of these modules in details. The algorithm begins with the image source module. It provides a unified image output format independent of where the image originates. Images may come from a camera, from local files, or from external code. This abstraction ensures that downstream modules behave identically regardless of the image source. The pixel format must be specified as it defines the output image type. Mono 8 is used for grayscale output, while RGB24 is used for full color images. If color data is not required, a color camera can still be configured to deliver grayscale images, of course. Depending on the selected image source, additional configuration options become available in the module settings. We will review some of them. The local image mode is useful during early development and algorithm prototyping. You can load images one by one or select entire directory to load all images at once. This short video shows how images are loaded from files. The folder monitoring option updates the image list automatically and can trigger execution when new files appear. The Save Image option stores the selected local images inside the solution file, adding to the portability. If it's disabled, only the file paths are saved, not the image data itself. Of course, it has positive impact on solution file size. So if you want to keep it small, you don't want to include images. But if you want to make it portable, it can be convenient to have images included. Auto switch option lets module advance to the next image on each execution cycle. The last one, stops option, prevents cycling back to the beginning of the list when the end is reached, and so on. There are many options. Camera mode retrieves image frames from a linked global camera object. On this short example, you will see how this global camera is added and how to configure image source module to acquire images from the camera. Exposure and gain are available directly in the image source module because they are essential for brightness control. These parameters can be set in the module and propagated to the camera. They can also be linked to variables set by other modules or by external communication, enabling dynamic adjustment of brightness while the procedure is running. The output mono 8 option allows the module to output a grayscale image in addition to color image when the camera is set to RGB mode. This is convenient as many modules in locating and defect detection categories only support grayscale images, so you will need grayscale image anyways. At the same time, you may want to use color image for some of the color inspection modules. And as you see, there's even a simple stitching option available with this image source module, but we have far more advanced image stitch module provided separately in VisionMaster for more refined control over how the stitching is performed. Locating tools are responsible for finding stable and repeatable reference features in the image. Their purpose is not measurement itself, but reliable positioning so that all subsequent processing steps operate in a consistent coordinate context. Depending on the application, locating can be based on learned templates, geometric features, or edge information. And the selected approach directly affects robustness, accuracy, and overall system stability. So it's important to choose the right tool depending on the requirements and conditions. Talking about template matching, VisionMaster provides several modules, each optimized for different locating requirements. These modules fall into two main categories: contour-based matching and grayscale-based matching. Contour-based approaches, including fast match, high precision match, and contour match, rely on extracted edge and contour features and are generally preferred when stable geometric features are available. So you have more or less the same pattern, visual pattern, which is available in the image. This is our case, and you will see it in a moment. Grayscale-based matching uses intensity distribution instead of edges, and it's suitable when contours are weak or unreliable across series of images, of course. Among these options, contour match offers a balanced combination of locating accuracy and matching efficiency. And it's therefore selected for this sample solution. So you see this diagram on this slide allowing you to choose the most appropriate template matching module depending on your scenario. Of course, this is the last verdict, the last decision should be made based on result obtained in practice. But this is a good starting point to choose the module to try the first. Here we see the interface for managing contour match templates. Templates can be created, edited, imported, and deleted. The template settings window provides a range of tools for defining the template area and drawing masks. You see it on the right side of this slide. The focus is on selecting meaningful contour features while excluding irrelevant image regions, masking them out. The template center defines the positioning reference. Parameters such as contour scale, matching accuracy, edge sensitivity, and the minimum number of chained contour points can be adjusted to achieve the most stable and accurate result. Multiple templates can be created within a single module to handle target variations. They are checked in sequence. So be mindful of creating many templates. It will have a penalty on performance. Contour match run parameters control how strictly a target is evaluated against the template during module execution. The minimum match score defines the required similarity level and helps suppress false positives. Limits on the number of reported matches and overlap handling control result filtering, while match polarity determines whether edge direction is taken into account. These parameters are typically fine-tuned after the template itself has been defined. And there are more options. Here, the allowable scale and rotation of the target relative to the template are defined. The scale range limits how much the target may grow or shrink, while the angle range specifies the permitted rotation during matching. By default, it is set to a rather narrow range of 90 degrees, and you may want to actually increase that range if you don't know how much your target is rotated. Overlap handling determines how closely multiple detected targets may overlap, with lower scoring results discarded when the threshold is exceeded. Usually, it's the object which is in the back, obviously. The threshold type defines how edge detection sensitivity is determined, whether derived automatically from the image taken from the module or set manually. So there are three options: automatically from the image, directly from the model, or some fixed value. And essentially, it will define the sensitivity and accuracy of entire matching, because it has to find these edges. And the next module we'd like to discuss is position fixture. Its role is to convert the locating result into a stable reference for subsequent processing. A reference point must be created explicitly using the same image that is later used to draw ROIs for downstream modules where fixturing will be applied. This reference is created once and then reused. Based on this reference, the module dynamically adjusts points and regions of interest so that subsequent operations remain consistent even when the object shifts or rotates within the image. Of course, it could have been done, manually, but it's just a matter of convenience. So this module greatly simplifies creation of scenarios where precise setting of ROI is important for proper finding of specific features, image features. And again, this is exactly our case. At this point, the algorithm moves from locating reference features to detecting geometric elements in the image. Geometric search tools are used to find primitives such as lines, circles, or rectangles, or maybe ellipses, based on edge information. They rely on caliper-based edge detection, where intensity transitions between darker and brighter regions are analyzed to determine precise feature positions. These tools are typically applied after fixturing, so that geometric features are searched in a stable coordinate context. And you see here is an example of how these edges are detected. So that's what you see. That's your two-dimensional image on the left, one-dimensional on the right, and this is intensity diagram. Use it to find these edges. Talking specifically about the line search module, we first look at the basic parameters. The module detects straight edges within a defined region by analyzing grayscale transitions between darker and brighter areas. The position, orientation, and size of ROI are critical, since they directly influence which edges are considered during detection. The module supports both drawn and inherited ROIs, as well as exclusion regions, and can follow the reference established by positioning fixture when it's enabled, of course. Continuing with line search configuration, these parameters control how edge points are detected and filtered before a line is fitted. Edge polarity defines whether transitions from dark to light, light to dark, or both are considered. The edge threshold and filter size influence detection sensitivity and robustness, especially when edges are weak or blurred. The ROI is divided into a number of caliper intervals, and within each interval, an edge point is detected. These points are then fitted to form a straight line, while the reject number specifies how many outlier points will be excluded before fitting is attempted. Actually, these points may have only a small deviation, but still, if you will use this reject number set to non-zero value, some points will be discarded. And the video now brings together the steps described so far into a single working flow. Images are loaded from files using the image source module. Then a contour match template is created uh, based on that cross mark to establish a reliable reference feature. Then the position fixture module is added, and it's executed to populate its input data, after which the reference point is created. This sequence is important since the reference must be defined from valid locating results. A line search module is added, and its ROI is drawn using the same reference image. As you can see, we didn't advance to the next image. With default settings, the detected line may occasionally be detected in the wrong position. You see it here. By adjusting the parameters to detect the first edge instead of the strongest one, and by reducing the edge threshold, the detection becomes stable and repeatable. You can see it right now. Okay, let's continue. Up to this point, the focus has been on reliably locating reference features and extracting geometric primitives. The workflow now shifts from detection to measurement. Measurement modules such as point to point, point to line, line to line, line to circle, and other similar combinations use the located points and lines to calculate distances and angles, converting geometric information into quantitative results. The point P2L or point to line measurement module measures the perpendicular distance from a point to a line by constructing the perpendicular projection of the point onto the line. If the projection lies outside the line segment defined by the line start and end points, the line is automatically extended, so the foot point may appear outside the original segment. The vertical distance is defined as the length of this perpendicular, and the angle represents its orientation in absolute image coordinates. The module directly subscribes to point and line results from preceding modules. And line-to-line measurement module evaluates the geometric relationship between two lines, obviously. The absolute distance between the lines is defined as the average of four perpendicular distances measured from the start and end points of each line to the other line using the same point-to-line principle described earlier. The module also computes the intersection point and the angle between the two lines. The intersection point may again lie outside the image area and its coordinates can be negative in some cases. If the lines do not intersect, the intersection point coordinates are set to 0, and the reported angle is either 0 or 180 degrees, depending on start and end points of line segments. The module can either perform its own internal line search with parameters resembling line search module parameters, or it can directly subscribe to line results produced by upstream modules. And that's exactly how we use it. in this sample solution. At this stage, the measured values are evaluated against defined acceptance criteria. The condition detection module compares distances and angles produced by the measurement modules with reference values and tolerance limits. Based on this comparison, each condition is classified as either pass or fail. This step converts raw measurement results into meaningful inspection decisions that can be further visualized, logged, or forwarded to some downstream system. In the final step of the solution, measurement and evaluation results are prepared for output. The format module is a general purpose tool for converting multiple input values into a formatted string. It can combine custom text with values subscribed from previous modules and supports line separators as well as array formatting when multiple results must be represented in a structured way, maybe coordinates. In communication scenarios, it is commonly used to prepare human-readable output strings or lightweight message payloads before sending data to external devices. The resulting string can be displayed on screen for an operator, saved to a text file, or passed further outside the VisionMaster environment. This concludes the overview of VisionMaster basics and the measurement workflow. We have seen how a complete solution is built, from image acquisition and reliable locating, through geometric measurement and evaluation, to final result formatting. Thank you for your attention. Now it's time to your questions.